Hello! Today I would like to have a look at this Coleman Rechargeable QuickPump. I was asked to troubleshoot this thing because it stopped working. I was told that it gradually lost power and now it appears to be completely dead. So it does absolutely nothing, despite of having been plugged in for quite a while, and the power supply seems to be fine. Here is this charging port, 6 volts DC, and I see this sign here, which means it has lead acid battery. Very old school and probably is completely dead. So let's take this thing apart. Alright, I removed the screws and some of them are stuck in the holes, but it doesn't matter. And I had to cut with a sharp knife this label on the bottom and these two rubber strips. And here we are. Let's have a look. It looks super simple. Just a battery, a connector, a switch, a motor and a fuse. That's it. And here is the other side of the battery, 6 volts, 4.5 amp hours. And it shows about a volt on it with no load, and it drops to 0.6 when I switch the pump on. So we need a new battery, obviously. I disconnected the battery, and it would be a simple matter to buy a replacement. I've seen they are about $10 delivered on eBay. But this project doesn't sound very interesting. After all, lead acid is an ancient technology, and pretty much the only advantage is price. So let's try to upgrade this pump to lithium-ion. Look at this. I have a pile of battery packs from old laptops. So let's try to salvage lithium-ion cells from one of them. Here is one of the biggest parts I got, and I ripped it apart, and look at this. We have 12 nice lithium-ion cells, and they're all sitting at about 3.6 volts, which is a very good sign. So this pack has a 4 series 3 parallel configuration, which gives us 14.8 volts and 6450 milliamp hours, which means one individual cell is 2150 milliamp hours. And the cells, I believe, are Sony, and the model is US 18650GR, and the version is G5. So let's see how many cells we can pack into this size. So the width is perfect, and this way we can put 5, and this way we can put 2 rows. So we can fit 10 cells in 2 series 5 parallel configuration. What about the voltage? This battery has nominal voltage of 6 volts, and usually it is charged up to 7.2. And these cells have nominal voltage of 3.7. So we need to put 2 of them in series to get 7.2 nominal, and they are charged to 8.4. So 7.2 nominal is a bit higher than 6, but I think the motor should handle that just fine. What about the current? Can these cells handle the current we need for this pump? I checked this fuse and it is 15 amps, so the actual current must be much lower than this. I would guess something around 10 amps. Unfortunately, I couldn't find datasheet for these cells, but I found a technical handbook from Sony mentioning this model, but unknown version. And here they are talking about discharging, and looking at this graph, which goes up to 2000 milliamp hours, I would guess that they are talking about some older version. I believe version G3 had capacity of 1800 milliamp hours. Our version G5 is 2150, and this older version, according to this graph, could handle up to 4 amps, which means our version G5 probably can do better than this. And we are going to parallel 5 of them, which will give us up to 20 amps of current, but don't forget these are used cells and we don't want to run them at the maximum. So if the pump is running at 10 amps, this is going to be about half of what the cells can do, which sounds good. Alright, I took the pack apart, and these cells are still attached, so we can bend them over like so. Careful not to short them here. Before we proceed, let's test one of the sections. First we need to charge it, so I connect it to a lab supply, which is set to 8.4 volts and 2 amps. That's the maximum it can do. And let's go. So now we are in constant current mode, when the current is limited to 2 amps and voltage is rising. Once it hits 8.4, then it will go into constant voltage mode, and the current will keep decreasing, and once it gets pretty low, let's say some 100 milliamps or so, then it's fully charged. So we are approaching the transition from constant current to constant voltage mode. Look at this, CC means constant current. Oops, and it just switched to constant voltage mode and current started dropping. Alright, the current dropped below 100 milliamps, so we can assume the battery is fully charged. Let's give it a full discharge test. I set the current to 6.45 amps, and this is the current at which the battery should last exactly 1 hour. Let's go. I will record the data on my computer. I will not go into details of this. I've done a few videos about battery testing before. And here is the result of the test. The battery didn't last for an hour, it lasted for 48 minutes, which is 80% of an hour. And I think it's not too bad at all. And in fact, the manufacturer doesn't rate the batteries at 1C. I believe I saw mentioning somewhere in the documentation that the nominal capacity is determined at 0.2C. It's not going to be dramatically different, but it can easily give another 5 or maybe even 10%. And the only date I found in this battery pack is on the plastic cover, and it is 7th month of 2004. So this battery is more than a decade old, and it's still about 80% of the capacity, and maybe slightly better than that. I'm quite happy with the result. And I run the same test for section 2, and the result is exactly the same, 48 minutes. And the graphs look a bit different here at the beginning, and this is just because in this case I first started the recording and then applied the load. And in this case I applied the load first and then started the recording. It doesn't matter at all. It's time to put together our new pack. The cells are discharged after the test, which is perfect for this phase of the project, but I still need to be super careful. I don't want to short anything. There is still a lot of energy left in the cells. I need to cut off 2 extra cells and connect everything into our desired 2 series 5 parallel configuration. Alright, some double-sided sticky tape there between the cells and this tape around to reinforce, plus careful soldering, and the pack is ready to go. Let's compare with this old battery. The size is perfect. It's a tiny bit smaller, which is good, and it's about twice the capacity of the old battery. The laptop battery pack had this battery management system in it, and by the way, I looked closer at this chip and I think I see the date code, 26th week of 2004, which confirms the date I found on the plastic cover. What's the purpose of this management system? It does many things. It protects the battery pack from overcharging, over-discharging, overcurrent, overheating. It balances the cells during charging, and this one is also smart. It means it keeps track of many things, of level of charge, for example, health of the batteries over time, and communicates all that information to the computer, so we can see in particular a nice battery gauge on the screen with the current state of charge and predicted runtime and such. Ideally, we need something like this for our pack. It doesn't have to be this smart. In particular, what we need badly is over-discharge protection. Let's say there is no protection and we run our pump until the motor stops. This would almost certainly discharge the cells below the allowed limit of 3 volts per cell. And we can even forget to turn the pump off at this point, and this will run the cells down to 0, and one such incident can ruin the pack easily. I looked on eBay and I found this module, which looks suitable for our purpose. It's designed for 2 lithium cells in series. This 2S indicates this, and the voltage is 8.4 volts. And it can handle up to 15 amps. Here's our over discharge protection set at 3 volts per cell. It also does over current protection, which is set at 25 amps. Unfortunately, as I understand, it doesn't do balancing of the cells during charging, and it also doesn't do any thermal protection. But it addresses our primary concern about over discharging. It's a small module. According to dimensions here, it can fit on top of the pack like this. And the price is $9.95 with free shipping from China. I will place an order. The only problem that delivery will take a long time, perhaps a couple of weeks or so. In the meantime, we can test without it. For thermal protection, I'm going to use this thing. This is a thermal fuse which opens at 100 degrees C, which is 212 degrees Fahrenheit, and it can handle up to 15 amps. It is tricky to solder thermal fuses, so I crimped the ends instead using the crimp connectors provided as a part of the package. And I put this fuse into the space between the cells. Added some foam padding to compensate for the difference in size. Look at this. It seems like some part is hidden under the heat shrink here. Perhaps a diode. We don't need it in our new configuration. Connected everything except the protection board. Let's give it a try. No problem at all. Let's measure the current. I'm going to use this current clamp to measure the current. And let's turn on the min-max mode to capture the spike. So what we've seen is that when the pump is idle, the consumption is around 13 amps, and when I block the air, the current consumption actually drops to about 8 amps. And let's see what the spike was. Wow, the spike was around 33 amps. I captured the current spike during the startup, and according to this measurement, the current was 31 amp, and it dropped below 25 amps, probably around 150 milliseconds. So this current spike during the startup can be a problem with our protection module. The limit is 25 amps plus minus 1, and the delay is 5 to 15 milliseconds. So if our current jumps above this to 31 or 33 amps and stays there for 100 milliseconds or even more, that can trigger our overcurrent protection. So now I'm not sure if this module will handle our situation properly, at least without some adjustment. We also need a charger for our pack, and preferably we need some lights indicating charging and end of charge. I looked on eBay again, and I see this cheapest option 376 with free shipping from China. A small charger which can only give 1 amp, and it has LED light on it. So it's the cheapest option, and it will take a long time to charge, but it should do the business. The next option is this one, for $9.95 and free shipping from China. We can get 2 amp charger, and I checked, it has LED light on it. And for $17.95 we can get 2.5 amps version, and they even show LED indicators right here. And looking at the pictures, I think all 3 chargers I just shown have the same type of connector, and one of them has these dimensions in the description, and diameters inside and outside look just perfect, but this 10mm length seems to be a little bit too short. So we might need to replace the connector. Here I have a connector which is 10mm long, and let's try. You see, it barely reaches this point of contact. And here I have another one which is longer, about 12mm. And let's try this one. So this one is just perfect. Let's have a look at some technical challenges involved. When I tested the battery, I connected it using these short and thick leads directly from the terminals in the power supply to the battery terminals, and everything was great. Now I have everything hooked up as it will be in the finished product, which means through this thinner and longer cable, through the connector, through some internal wiring, through the switch and through the fuse and the thermal fuse we have installed. So, according to the power supply, we are in the second phase of the charging process, which is constant voltage. Which means we reached 8.4 volts and the current is decreasing. But let's measure what's happening on the battery. So directly on the battery terminals we have 8.11 volts. So we didn't really reach the second phase of the charging yet, and we should be pumping maximum available current into the battery at this point, which is 2 amps in this case, but we are not doing so because of all this voltage drop on the wiring. And of course, when the current decreases, the voltage drop on the wiring will decrease as well, and eventually the battery should reach something close to 8.4, but it will take much longer. And let's measure this voltage drop. So we'll start from the negative terminal right here to the negative on the connector, and we have 76 millivolts, and from the positive to the positive here should be about the same. Yeah, sure enough, 76 millivolts. So we are dropping around 150 millivolts on this wire alone, plus some additional things like the switch, for example. So we have voltage drop of 45, let's say, or even more, 50, about 50 millivolts just on the switch. And by the way, I don't really understand why the charger should be connected to the battery through the switch. I guess it was done to avoid overloading the charger if we happen to turn on the pump during charging. But first of all, this negative wire from the motor gets disconnected in this connector when we insert the plug, so the pump wouldn't run anyway if the charger is connected. And second, I just don't see why that would be any problem at all. With the proper charging, which is current limited, there should be no problem. It will just contribute the current it can contribute, and not more than that. Should be just fine. But unfortunately the original charger is lost. I cannot verify what kind of charger was that. I guess it was not a proper current limited charger, and they somehow got away with just simple power supply. So I think I will make a permanent connection here, just solder a jumper across this switch, because disconnecting the charger is not really necessary, and additional voltage drop here just slows down the charging. Alright, I have done just that. And by the way, I also don't understand why the charging was done at 6 volts here. First of all, lead acid batteries should be charged to about 7.2. And second, remember there was a diode installed here, and yes, I checked, it was a regular diode with a voltage drop of 0.6 volts or so. And that means to charge the battery to 7.2 we needed about 7.8 at the connector. So I am under the impression that this whole thing was not done properly. It was done super simplistically to reduce the cost as much as possible. Speaking of this voltage drop on the charging cable and the connector and such, making the charging process less efficient, there is a way to deal with this problem. Imagine we had a small charger which would fit inside the unit, let's say here, and it would accept an unregulated voltage as an input, let's say from 9 to 12 volts of sufficient current, let's say 2 amps, and the output would be connected inside the unit from the charger to the battery with a short permanent wires with no connector involved. So in that case the voltage drop on the external wire to the unregulated power supply and the connector wouldn't matter at all. But I don't know where to get such a charger. It can be certainly designed, but that's a little bit more involved that I want to deal with for this battery upgrade project. So I think I will just buy a cheap lithium-ion charger on eBay, and it's gonna be good enough. About 2 weeks later, this battery management module has arrived. Let's give it a try. And here it is, connected to the battery pack. It is arranged like so, and this center tap, which is yellow here, it doesn't have to be thick. This is just for sensing purposes, so that module can measure the voltages on each cell individually for overcharging or over-discharging protection purposes. Note that when a module like this is connected to a battery pack for the first time, the output is disabled, and it's done for a good reason, deliberately. It's much safer this way. It allows safe installation of the finished battery pack with the module into an end product without a fear of shorting anything, and the output is enabled only after a charging voltage is applied for the first time. Everything is wired up and initialized by connecting the charger, and it's not working. It seems like the overcurrent protection kicks in. Let's measure with the scope. I'm using the same current clamp, and the scope is set up and is waiting for a trigger. Let's go. Here is what I captured. About 31 amps for about 15 milliseconds, and as you can see, the overcurrent protection circuit is very effective. So this battery management module is not quite suitable for the application. I really wish it could be a slightly higher current module, let's say current handling of 18 to 20 amps, with this overcurrent protection around 35 amps. That would be ideal. And maybe I can even adjust this overcurrent protection threshold by changing this shunt a little bit. I've done a lot of experiments, and let me quickly describe what I found. So the easiest way to limit the current was to add some resistance, and I had to add 150 milliohms before the pump could start. This resistor is 50 milliohms, 15 watts. I had to add 3 such resistors, and I was not happy about this result, because these 3 resistors would dissipate too much power, so too much power will be wasted, and too much heat will be dissipated inside the enclosure. So I started adjusting the current shunt. So here I soldered one link in parallel to the existing shunt first, which allowed me to lower the resistance to 100 milliohms. Then I added one more link and the solder bridge right here between 2 points, which allowed me to start the pump with just one resistor with 50 milliohms. But then it occurred to me to test at the extreme, when the voltage is the highest. So I charged up the battery in full, and now it cannot start again. Let's see, I'll look into this hole. So the motor tries to start and cannot. So it receives this initial pulse of power before the overcurrent protection kicks in. The good thing here is that I'm confident that I didn't defeat the overcurrent protection entirely. It works perfectly, so I managed to shift the threshold quite a bit, but still not enough. But now I need to add a little bit more resistance so that pump could start with the fully charged battery. So I added this resistor, which is 10 milliohm resistor, so the combined resistance is 60 milliohms, and the battery is fully charged, and now the pump can start. I'm not quite happy about this result. Let's quickly calculate how much power will be dissipated on these resistors. Our current at steady state is about 13 amps, and the power is I squared R, so 13 amps squared times 60 milliohms, we get roughly 10 watts. So 10 watts will be wasted, and the resistors will get hot inside the enclosure, so I'm not quite happy about this. We can improve this situation by having the resistor in the circuit just for a brief period during the startup and then get rid of it. Let's consider this circuit. Here is our motor, here is our battery, and here is our switch and the resistor. So the current flows like so. And suppose we arrange a relay across the resistor, and some sort of a delay circuit will receive power after the switch. So when the switch is closed, this thing gets powered up, and after a brief delay it energizes the relay, and relay closes and gets rid of the resistor effectively by shorting it. But it's not as easy as it seems. Consider this relay, for example. I just happen to have it. It's rated at 15 amps, and I found the datasheet for it. Let's have a look. Here is the datasheet for the relay, and have a look at this. Contact resistance 100 milliohms max at 1 amp. So we are trying to short 60 milliohm resistor with contacts which are rated at 100 milliohms resistance, so the overall resistance will not drop too much, and probably we can find a better relay with a lower contact resistance, and most probably it's gonna be more massive, but I think there is a better way. A better way would be to use a power Mosfet transistor as a switch, and in this case we don't even need our resistor. The transistor can be open partially for a brief moment, and then it can be turned on completely and present very low resistance. Modern MOSFETs can have a very low resistance when completely turned on, as low as a few milliohms. The best one in this sense I have is this one, and it has 14 milliohms resistance when fully turned on. Here are the specs, and it can handle 70 amps at 60 volts, and the drain to source resistance in the on state is 14 milliohms, and it can handle up to 175 degrees C temperature. This 14 milliohm value is maximum guaranteed, but with 10 volts applied to the gate. We don't have 10 volts in our circuit. We have from 6 volts with the completely discharged battery to 8.4 with completely charged battery. So in our circuit the resistance is gonna be slightly higher, but probably good enough anyway. I'm thinking about a soft start circuit like this. Again, this is our battery, this is our switch, and this is our motor. And in the negative path we can have this MOSFET with the gate connected to this simple RC circuit. When the switch is closed, initially the capacitor is completely discharged, so the gate is at 0 volts, so the MOSFET is off, and then the voltage here will slowly rise and gradually turn on the MOSFET. And when it's fully on, it should present very low resistance, hopefully something close to that specified 14 milliohms. Here is our MOSFET on a small heatsink, And here's our source from the battery, and the drain is connected to the motor, and the gate through this resistor to the switch. And I didn't even need the capacitor, because MOSFETs usually have pretty high capacitance at the gate already. So let's have a look. Input capacitance is 2550 picofarads, which is apparently enough in our case. Let's go. No problem. And let's measure the voltage drop across the transistor. About 200 millivolts. And this means that our transistor has the on resistance in this case of about 15 milliohms, and the power dissipation is 2.6 watts. Not bad at all. I like this result. And here is what I see on the oscilloscope. The rise time in fact is very short, about half a millisecond. But it seems like this smoothing of the initial current spike is enough to make the overcurrent protection happy. Here we have almost finished pump. Let me zoom in on this transistor. So I didn't shrink these pieces of heat shrink yet, because I want to do some measurements. We'll get to that in a minute. And the 10 kilo ohm resistor is inside of this longer piece. What I wanted to measure is how much that voltage drop across the transistor changes when the battery gets discharged a bit and things get hot. So I have this multimeter measuring the voltage across the battery, and we have about 7.5 with no load, and this multimeter is measuring the voltage across the transistor. Let's go. What I also wanted to check is how hot things run, and I used to use this infrared spot thermometer by fluke for this purpose, and it works great. I highly recommend it. But now I got this, which is infrared camera, and I realized how blind I was without it. Let's check it out. So the pump is sitting on the edge like this, so that the inlet is not covered, and I will run it for a few minutes and we'll start checking. The charger has arrived. I bought the 2 amp one from China on eBay for $10, and yes, the connector is slightly shorter than ideal, but it works fine. In fact, there is that notch on the connector which corresponds to the contact. So it's held in place securely, and I don't think I need to replace the connector. Here is our finished pump, and I put a label here next to the charging port, as well as on the charger. using this label printer. Very handy tool, I highly recommend it. As always, thanks for watching, and if you like this video, give it a thumbs up and don't forget to subscribe to the channel. Thank you very much. Bye.